Let me start with my presentation at Oaktable World this year with the title Analysis of 3 AWR Reports. Whenever I talk about AWR reports, I want to make a few preliminaries, and actually this is a preliminary that I always need to make because it sets some context that I'll use later on in the talk also. So when you look at an AWR report, which is a fairly large and complex report, you obviously know it's reflecting what has been going on in a database, in this complex piece of software called the Oracle database. So judging or interpreting an AWR report really requires that you also know quite a few concepts of the architecture of the Oracle database, how Oracle operates, how Oracle services your database calls. That's really an important thing to know in order to understand an AWR report. But what also helps you in understanding an AWR report is realizing that the AWR reports is reflecting the workload that the database has been servicing and that was generated by your application. Yeah, so if you have some knowledge about the application that was doing this workload generation towards the database, that too really helps in understanding an AWR report. Finally, often you're looking at an AWR report because your application obviously has some kind of performance issue. You've generated an AWR report to analyze, to diagnose this performance issue. Knowledge about the issue is certainly helpful also when talking about and looking at an AWR report. Now, very often in the real world, these last two are unknowns, or at least not clearly known, unless you're dealing with your own environment and you probably know what your application is and what your issue is. But we often get handed AWR reports basically with the question, is there an issue or not? Or can you find some low-hanging fruit that we can fix? Is my application running optimally? Those kinds of questions. Yeah. Even when we get an AWR report with those kinds of questions, we often find issues. But that's beside the point right now. But actually, it's really these three things that help you in interpreting an AWR report. Knowledge about the Oracle database, knowledge about the application that was generating the load that you're looking at in the snapshot interval of the AWR report, and the cause of why you're looking at the AWR report, the issue that gave rise for you to generate the AWR report. So with this preliminary out of the way, here's my agenda. I would like to make sure that we are all on the same page about one important concept of the architecture of the database. And that concept is called DB time. So I'm going to spend, I think, 3 or 4 slides on this concept. Then I'll introduce you to an approach that we use quite often in the real world performance team in approaching an AWR report that we are being handed. That's just a single page. I'll explain how we approach it, and then I'm going to use that approach in the 3 examples, which will be the majority of the time of my talk. So DB time, probably most of you all know this. It's the total time spent by foreground events, either actively working or actively waiting, but in a database time, spending time in a database time, in a database call. And if I use the word foreground session, I mean a database session created by your application, which is in contrast with background sessions. We also have time spent by background sessions, database writer, log writer, etc. The time spent by those background sessions is not included in DB time. DB time only accounts or gives you a figure telling you how much time have the foreground sessions been spending inside the database during this snapshot interval that we're looking at. So visualizing this, here I'm depicting one foreground session that time-wise, going from left to right, is servicing a couple of database calls that are issued by the application code. Yeah? So the browse book module might issue a query, it retrieves a couple of books back. Then further on in the application, you might go down into the database from your application to retrieve the reviews of a book. So at these points where I have the green bar here, database time is being accumulated. When this foreground session is not servicing a SQL or a stored procedure or what have you database call, so that's the black bits of this arrow, no database time is accumulating in this foreground session. Yeah. So the sum of the green bits is the database time of this foreground session. It's basically just counting the time spent inside the database in a database call being serviced by this database session. Now, in our database, we have multiple sessions. We don't just have one foreground session. We have multiple sessions that are being created by the application or by the underlying connection pools of the application. So the database time is the sum of the DB time over all these foreground sessions. And it's a very important metric. It's the #1 metric that we're looking at when you're looking at an AWR report. The last thing that I would like to mention is that database time roughly consists out of 3 classes of time. The first one is CPU time. Whenever your foreground session is executing instruction code of the Oracle kernel, I'm depicting that with green here. The second time when we can accumulate furthermore on the DB time is when the Oracle kernel issues an IO request, and we're waiting for IO. I'm showing that as blue here. So that's an active wait event. And then we have a whole lot of other waits. So from the top level, database time consists of CPU, waiting for IOs, or waiting for some other database related wait event. For instance, waiting for a log file sync event to complete. Now, you want to understand the database time during the time period that the AWR report is reporting upon, because that is telling you where the database has been spending its time. And an AWR report includes a highly detailed account breakdown of where the database has spent this database time. Yeah? And the database time is the #1 metric that you want to look at, especially the breakdown of it, to find if there are components in database time that you might get rid of or that you might optimize away, thereby making the database working more efficiently on the calls that are being submitted by the application. Yeah? So database time is really the #1 metric that that you need to be aware of when you look at an AWR report. So with that out of the way, what's the approach that we often take when we get handed foreign AWR reports? Whenever we get an AWR report, we start looking at some key areas first. Again, this is a huge report. It's a very big report with lots of information. And I'm going to reveal in a second what these key areas are. But we first start looking always at these key areas. Most of the other information on the AWR on the report is detail that we don't look at unless something from the key areas is pointing us towards it. And I'm going to demonstrate that with the 3 AWR reports. So what are these key areas? The key areas are the top 2 sections that you see on an AWR report. That's the summary of the environment that talks about what kind of environment is this, what type of Oracle release, etc. What kind of server are we talking about? And the section right below that, the load profile. Then, because we often see unknown environments, we first go down to the init.aura. Check the init.aura, see if there's any specials in the init.aura. This helps build up some context about this environment. And often after having seen the init.aura, only then we go to the top foreground events, which is very likely probably the first section that a lot of people go to when they look at an AWR report. And this is our #3 or #4 section that we go to. And we can judge the top foreground events much better having done the summary of the environment, the load profile, and the init.aura always at the start. And then finally, we check the time model. The time model sometimes reveals things that the top foreground events don't reveal. Yeah, so I'm going to use that approach with 3 AWR reports. Let's start with the first one. And I've entitled the first one rack with all the classics. Now, when we look at a rack AWR report, we prefer an AWR report per instance. And the reason is very simple. The rack version of the AWR report, where you have, if you have a two-node rack environment, all the information condensed into a single report is just much more difficult to read. It's much more easier to have two tabs open and have a rack report of each node separately and switch between them and have a look at the various sections. So let's start with the first key area, the summary of the environment. So I'm showing here the top section of the rack report of instance 1 and the rack report of instance 2, because this was a two-node rack environment. So it's a fairly recent release. Obviously it's rack. We're not using multi-tenant here. Both systems have 20 cores on board. They both have over 2,000 sessions connected into the database. Yeah, over 2,000 foreground sessions. This immediately raises not necessarily a red flag, but gives us the idea that this system might be oversubscribed. Now, what we mean by oversubscribed, I'm not going to exactly explain that right now. I think that we have a video out there on YouTube that describes this concept, and very likely you are able to find a blog post really soon from our team where we detail what we mean by oversubscription. The other thing that we see now here is that this rack report covers 206 minutes. That's actually a rather large interval for an AWR report. Normally you would look at smaller intervals. You would look at an interval that pinpoints the issue that you want to investigate. But here we're looking at an over 200-minute interval. Both instances have accumulated sort of like the same figure of DB time. This now tells us that both nodes are equally busy in terms of DB time. And what we also see is that the DB time is roughly a factor 30 of the elapsed time. So on average, of these 2,000 sessions, 30 were active, 30 were servicing a database call on average. Which is immediately confirmed in the second key area, the load profile. The DB time per second gives us that number also. So the 34 here and the 30 here tells us at any point in time, on average, there were 34 sessions active here. There were 30 sessions active here. Now, I mentioned when you're doing DB time, it can be CPU, it can be IO weights, or it can be other weights. In the load profile, we also see what bit of the 34 was CPU. So per second, we were burning 3.6 CPU seconds on this node, 9 CPU seconds on that node. Whereas we had 20 cores. So we can immediately conclude that the database probably still has CPU left over to process more, assuming that there aren't running any other instances on these two nodes. The other thing we notice is that there's quite some global cache activity going on both nodes. It's a very chatty application. Per second, we're getting 21,000 calls from the application servers into the database over here and 50,000 calls over here. And there's a difference in the parsing aspect between these two nodes. There's a noticeable more parsing going on the second node, almost 4x, and not just soft parsing. There's also hard parsing going on the second node, which is hardly present on the first node. And finally, we have a fair amount of transactions going on, even some rollbacks. Just noticing this here, maybe it's useful later on, maybe not. But we have some more context now. This fairly busy system, not using a lot of CPU. So the majority of the DB time is waits. I'm going to expect to see waits in the top foreground events later on. But we're not going there yet. We're first going to the init Aurora. And this init Aurora is actually extremely clean. It's an init Aurora. I've never seen a cleaner init Aurora like this one. in all the AWRs that we get handed, because there's 0 underscores in here, and there's only really the most necessary things are in there. There's only 2 things that I might find noticeable here, and that's open cursors is set extremely high. Remember, this is a setting per session, so why would any session want to have 10,000 cursors open? Maybe there was a session leaking issue sometime in the past. If I go back 2 slides, we can see that there definitely is not a session leaking issue right now, because the average open cursors for a session here has never gone above 2. Yeah, but maybe there was an issue sometime in the past. This is just noticeable here. The other thing is the cursor sharing, which is set to exact, which is the default. So, and it's still in the init Aurora. So they may have been playing around with cursor sharing setting to force, maybe to address these hard parsers at some point in the past, but they aren't at the moment because it's been set back to the default. Yeah. So it gives me some more context about it. It's often a bit of a it gives me some history of this environment, because often things are left over, and as you can see, there's 2 things left over here in this init drawer. So now I go to the top foreground events, and we already knew that we're going to expect to see wait events here. And what do we see? So this is the first node, this is the second node. On the first node, we have a major issue in the area of index contention. A big chunk of the DB time, 25% of the DB time is spent waiting for index maintenance going on, initiated by another session, and a current session waiting for that session to complete DB tree index maintenance. We had a fair amount of transactions going on, so we were expecting to see the commit-related wait event, the big one, the log file sync, and we see that actually on both instances. So, but that's not something to worry about, because we're doing commits, we're doing transactions on this system. And the second instance is actually pretty normal in terms of a transactional system. You see DB CPU is the top one, and then commit as the second wait event. Now, the other thing we notice is that there's global cache related wait events across the board on both instances. Again, we were already, we're not surprised by that, because the load profile already gave us that detailed information that we had a lot of global cache activity going on. Now, finally, I go to the time model. And in this case, I only go to the time model of the second instance, because there was parsing going on there, and the first instance didn't have any interesting in the time model. So the time model now enables me to judge how bad is this heavy parsing, this 4x more parsing on the second node, and the hard parsers, the 37 hard parsers per second going on. Yeah, it gives me an idea what amount of DB time is being used by these hard parsers. Yeah? Now, going back here, we didn't see any shared pool latch related events. So these parse times are probably all CPU. There aren't any waits going on in this area, parse related waits going on. So very likely this is all CPU. So I can now see that, well over 10% of the CPU on the second node, we could gain if we fix this parse issue. Yeah? It gives me an idea of how much could we gain by fixing that parsing issue. So that's the time model. Yeah. So now we're done with the key areas, and we're going to ask how to proceed. Well, this environment is dominated by waits. So we're going to follow up on those first. And then we may also look CPU-wise at fixing that parsing issue on the second node. So the weights were the NQTX contention on the first node and the global cluster weights on both nodes. So let's go to the NQTX index contention first. Luckily, this was a 12.2 AWR report. And a 12.2 AWR report has this top SQL with top events section, which immediately pinpoints the SQL ID that's being hit by this wait event. So this is an insert statement, and I've formatted the insert statement here. It's an insert into a table posting request, values, some next file from a sequence, and then some a bunch of bind variables. And it's actually a single row insert statement, which I can check if I go to the SQL ordered by executions. It's processing single rows. And it's being executed a lot of times. So here we only have the sample number, but if you go to the SQL sections, you see that this statement is being executed over 3 million times, obviously by different sessions, by different foregrounds simultaneously, and they are then hitting the index TX contention, which is a classic wait event that you will hit if you have multiple sessions aggressively inserting into a B tree on what's probably a primary key of this table. Yeah. Now, this being 12.2, we could probably try mitigating this by changing this into a smart sequence. Since 12.2, we have a smart sequence that uses the session ID and the node ID information to distribute inserts into this B tree, not only at the far right down bottom of the B tree, but at different sections inside the B tree. If you've never heard of it, you might want to go look up in the documentation what the release 2 smart sequence feature is. But this definitely also requires, I would also follow up on this in the sense that I would go back to the person who gave me this report and ask, can you give me a report of all the other indexes on this table? Very likely there are other indexes on this table, just to check maybe some of them are redundant, or maybe we can change a little bit in the architecture of the indexes that have been put on this table to maybe further mitigate this index contention issue. As for the second wait events that were going on both nodes, I'm showing here the SQL ordered by elapsed time, but probably a much more intuitive way to go to was, no, I'm not going to be able to do that now, was to go to the SQL ordered by cluster wait times. The reason why I'm showing up the order by elapsed time here is because it on node 1, it clearly shows this posting request insert as the #1 elapsed time contributor to DB time. And the point that I want to make here is that I often look at these two columns, %CPU and %IO. So these two columns tell me of the DB time that this insert statement has been generating, what percentage was CPU, what percentage was IO, and I can then deduce what percentage were other weights. Yeah? If these two do not sum up to 100%, and they obviously do not for this one, I can now deduce that almost 97% of the DB time spent by this insert statement was caused by those index TX contention. Yeah? So it's really a serious issue for this insert statement. And I immediately also now see the other ones that do not sum up to 100%. And you can verify that again by going to the ordered by cluster wait times, is 3 insert statements and 3 update statements. And those 3 insert statements, these 3 SQL IDs, they are executed on both instances simultaneously. Also the 3 update statements. Same SQL IDs over here and the same SQL IDs over here. So it looks like people have started using RAC for this application without putting any thoughts into data affinity. It can bite you really bad, and in this case it bites them really bad in the sense that if you don't put any thoughts into data affinity when you start using RAC, well, you're gonna very likely end up with a lot of GC activity and also the related wait events between that come with this. There's one thing that I want to talk about here. It's just something we notice here. You see this append hints? Insert into append. This is just wonderful. You can't think this up. So there's actually, I think there's 2 issues with this. It's an aside, but I want to make this because it was a beauty that we spotted in this AWR. So the first thing is Does this work? Obviously not, right? It's positioned at the wrong place. It should be positioned behind the insert keyword, not behind the into keyword. So this hint is actually ignored just for the reason that it's not injected into the SQL text at the right spot. Other than that, had it been injected here at the right spot, it would still have been ignored because we started ignoring the append hint for single row inserts. You would want to use the append hint if you use set-based inserts. Because in a single row insert statement, an append hint will insert a single row into an 8K block, and then the next insert will be into a new 8K block, which lies above the high water mark. Yeah? So we've introduced an append underscore values hint if you really want an insert statement to use a direct insert. But then you don't want to use this when you're not using the array interface for these bind variables. You only really want to use append values when you're binding multiple arrays of rows here, thereby filling a full one or multiple of 8K blocks at the same time. But this is an aside. It was just too beautiful not to mention. So how do we fix these GC-related wait events? Well, really, this can't be fixed without changing the application. That's the only answer that I can give in this at this stage. Yeah? If you want RAC to work well for your application, you will upfront need to have thought about designing your business logic to support RAC, which also goes hand in hand with designing underlying table structures to support that. Yeah? But let's take a step back. Do we really need RAC here? Remember, we were using little DB CPU on these both nodes that both had 20 cores on board. The operating system statistics detail confirmed this. Both instances are not busy at all. Very likely, if you were to switch off the second node and have all the load go to the first node, you immediately lose all the GC wait events, and very likely the first node can just can take the load as it is right now. Yeah, so this will probably run on one node a lot faster, just judging by what we see right now in this AWR report. Now, the last thing that the key areas pointed us to is the CPU spent on parsing. There was a lot of soft parsing going on, but also a bit of hard parsing on the second node. And the SQL ordered by parse calls confirm that we are actually doing a parse per execution. Yeah, which is not the best way to make use of the Oracle database. You can re-execute a SQL statement by just rebinding new values into the bind variables and then re-execute it. Now, since we were using JDBC, very likely there's a universal JDBC connection pool involved here. And a very easy fix could be to just configure JDBC statement caching on the application servers. Especially if these are WebLogic servers, it's very easy to configure the statement cache. And then the parse calls would immediately go down. You'd have to play around a little bit on how big the JDBC cache should be on every WebLogic managed server, but you can really easily mitigate the parses in that way. Finding the statements that hard parse on node 2 again requires follow-up. We can't identify these in an AWR report because they are not these SQL IDs do not show up in the SQL sections because they're all executed a single time with the hard parse single execute, and then at some point they probably age out of the shared pool. Yeah, so we would have to go back to the submitter and with a bit of querying in the shared pool in the SGA, we can probably locate these statements also and then request for those statements again to change the application and have them use bind variables. Yeah, a final comment that I want to make here is this is very common. Again, I mentioned this earlier. That insert statement was using row by row processing, the one that was being hit by index contention, but actually everything is using row by row statement, row by row processing. This is not the most efficient way to make use of an Oracle database, but alas, that's the way we build applications nowadays. The thing that I spot though is that there's one that very prominently always has 2 rows per execution. Now this just begs to dive into, in the sense that it would not be the first time that if I start looking at this SQL statement and I go back to the developer saying, do you know that this one actually, it's a select statement, queries 2 rows instead of 1 row? Oh, does it really? It shouldn't. Well, I looked at this SQL statement, and I think it's legit in this case because it's selecting from a customer table balance using a customer ID predicate, and it's selecting a balance ID and a balance type. So very likely for each customer, there's 2 balance records in this table. So it's probably legit that we have a 2 over there instead of all the ones that we see for all the other SQL statements. Yeah, so in conclusion, these 2 reports, why did I call them RAC with all the classics? Because all the classics are present in these 2 RAC reports, and by classics we mean the index contention, the excessive soft parsing, and even some hard parsing, the row by row processing, and no thought having been put into data affinity. Yeah? So you probably don't need RAC for this application. Other than that, open cursors were a bit high. There was a too large connection pool, but they are not biting us at the moment. So this was the first AWR. Now let's move on to the second AWR, which I have given the title, It's Not the Database. Now we were given this this AWR, and we did have a bit of information on the application. So it was said that this AWR covered a batch program that ran, and this batch program runs with multiple threads, and there was not a connection pool being used. Each thread had a dedicated connection into the database. And the question that we got with this AWR is SQLnet message to client my problem? Well, let's go and have a look. But again, we're going to use our approach, and then we'll figure out if that question is a yes or a no answer. So what's the summary of the environment in this case? It's an 11.2 non-RAC environment, 12 cores, 2 hour in the evening batch window time, 2 hours covered. And of the 2 hours, only 30 minutes were being spent inside the database. Yeah, so with the knowledge that I have about this application that has been given to me, I can now say, well, if this batch program is running with, let's say, 1 thread, then each thread is spending 25% of its time in the database and 75% of its time outside the database. So either in the application server or on the network. Yeah, but if this batch program is running with, let's say, 5 threads, then each thread is spending only 5% of its time in the database, because then I'll end up with 30 minutes in the database and 95% of the time outside the database. Yeah. So you'll start understanding why I've given this AWR report the title that I've given it. Now, if we look at the load profile, which is the second section that we visit, we notice that the 25% of the time, which is rounded up to 30% for some reason in the load profile here, is all CPU. Yeah, all DB time is CPU time. The operating systems detail confirms that we only have 0.3 CPU going on. This box had 12 cores, and we're only keeping 1 core 30% busy. That's what this tells me. And the operating system details tell me that indeed this database server is as good as idle. It's not doing much at all. Yeah. It's a chatty application, not as chatty as we saw before. Wow, this is very good. Yeah, so we have over 2,000 calls into the second, hardly any soft parsers, no hard parsers, really good. And a very low transaction rate going on. Init.aura in this case had nothing worthwhile mentioning, so I'm going to skip that. And now we're going to the foreground events. Now remember the question that we got. So the foreground events show us, again, something that we already knew because the load profile gave us that information, that all DB time was DB CPU. 100% of the DB time was DB CPU. Now, what's with this SQLNet message to clients? So I'm being hit by 14 million SQLNet message to clients. Is that my issue? Well, if you do the math, we had 120 minutes times 60 seconds times 2000 user calls per second, which was in the load profile. That pretty much brings us to these 14 million. So the math is right. Yeah. But of course, the big thing is it's only contributing 0.5% of the time into the DB time. So this is not your issue, and it's perfectly explainable, judging from the figures that we see in the load profile. Now, if we go to the time model, the last section that we always visit, we see that there is a big gap here. Remember, all the DB time was DB CPU. And we're only executing SQL, which can be confirmed if you go down to the SQL sections. But there's 700 seconds missing here, which is not explained in any of the other time model statistics. Yeah. This is a beautiful example of something that I talked about 2 years ago at Oaktable, where I talked about the overhead that chatty applications have. Now, if you have a chatty application and your select statements or your insert statements or what have you execute really fast, and in this case, they execute super fast, and they execute super fast for 2 reasons. Because the SQL ordered by execution sections shows us actually that we have a no row by no row approach going on here for some of the SQLs instead of a row by row approach. So looking at these SQL statements, they only need to go to a B tree. They only need to go look up a primary key in a B tree, and there's no table access involved at all. So they execute super fast, and the other ones sometimes go to the table to access a row via a row ID, and we have a couple of ones that always go to the table to execute a row via the row ID that was found in the index. But they all execute extremely fast also because of the fact that there's no parse. We saw in the load profile that the application behaves really well towards the database in the sense that it rebinds new values into the bind variables and then re-executes the cursors. If you have this kind of environment where select statements or SQL statements execute really fast and you're CPU bound, you can see the overhead that chatty applications have in the context switching area. Getting in and out of the Oracle executable in this time roughly takes 700 seconds. I've talked in detail about this phenomenon again 2 years ago. It's the knock-on cost of chatty applications, row by row SQL statements that also take time traversing down into the Oracle kernel and traversing back up out of the Oracle kernel before they hit the SQL engine. And if you want to know more about that, there's a YouTube film on the internet. If you just Google for my name, you'll probably find it really quickly where I talk and explain this issue in detail. But we can that's very likely if we would further look into this issue where these 700 CPU seconds missing originate from. Now, and this of course is really good. I would love to see more AWR reports where the statistic repeated bind elapsed time is the number 3 one. Yeah, I would want CPU and SQL execute on the first 2 spots and really would like this one on the 3rd spot. So that's really good. It's excellent. So we're now done with the key areas, how to proceed. Well, this now depends on what the issue was. We were not given an issue. We're only giving the question, is SQLNet message to client my issue? Well, we've came to the conclusion that it isn't for this AWR. So what's the issue? Is the issue that you can't get the database busy? Well, then increase the number of threads in your batch process because there's still plenty of room on the database server to do processing for your batch. Or is it that your batch, your application is just too slow? Well, in that case, you need to start investigating the time spent outside the database, yeah, because the majority of the time is spent outside of the database. 75% if it's just single threaded, and 95% if you are running with 5 threads. Yeah, but can we get a clue though, if this might be the issue or that might be the issue? Well, we can get a clue if we go into the AWR report and we look up the SQLnet message from client wait event, which is the wait event that tells us how long did a foreground session have to wait for another database call to come into this foreground session to be serviced. On average, once a foreground session has completed a database call, it has been waiting for 1 millisecond, which was very stable. If you look at the histogram, a little variance in the 1 millisecond. It had to wait for 1 millisecond for the next database call to come in from this batch thread on the application server. Yeah. Well, this is really small. It might be the case that if you were to test maybe the ping times between the application server and the database server in this case, that already is a big chunk of the 1 millisecond. Yeah, I suspect that most of this is probably network time and not business logic executing on the application server. This tells me that the threads on the application server are constantly calling the database once they have completed a previous call. So there's little to no business logic at all. It's a very tight loop, submitting SQL statements all the time. So we have a chatty application that's submitting SQL all the time, which is CPU bound. It's only using CPU on the database. The database is not doing much. The application threads have little think time in them. Very likely the majority of time is spent on the network. So if your issue is indeed the batch is slow, which we suspect now, then you need to maybe look into co-locating the application server in the same rack as your database server, preferably with a direct network connection in between, hopefully bringing the ping times or the network round trip times further down, because that's very likely the major contributor to the elapsed time of your batch threads. Of course, a much better solution would be to just move your application logic into PL SQL and be done with this network pinging and chattiness of your application altogether. But often that's not doable. So moving on to the last AWR, how outliers influence average wait times. Let's start with our approach again and start with the summary of the environment. This was a non-rack environment, 44 cores, and contrary to the AWR that we've just been discussing, we have a extremely high amount of DB time, given the only 15 minutes of the elapsed time of the snapshot window that we're looking at in this AWR report. Yeah. Dividing this tells us that we have 184 average active sessions going on this database instance. Well, if we have 184 average active sessions, 184 foregrounds working on a database call with only 44 cores, that clearly cannot all be on CPU. So I'm gonna suspect we're gonna see a lot of waits at some point in time. The load profile confirms the 184. And it even confirms now details further that we're actually only spending 10 seconds per second on CPU. Yeah? So of the 44 cores, only 10 are busy doing CPU. But we have 183 sessions actively either then waiting for I/O or waiting for some other wait event. The other thing that I want to mention here is that we have a fair amount of transactions going on. Again, this is a chatty application, etc. But we'll see further on that that's not to the point for this particular AWR. Again, we check the init.aura first. The only thing that we could see in the init.aura that was worthwhile taking a note of is that data guard has been configured for this environment, for this database. And it's been configured in the sync firm mode, which is the most expensive mode in terms of shipping your redo from your primary to your data to your standby environment. Now, are we now surprised that we see log file sync as the top wait event? No, we're not. Again, the approach often helps you in already understanding what you are going to see in the top foreground wait events, because we know we had a heavy transaction rate, 8,000 transactions per second. We know we have a standby and sync affirm configured. Well, the log file sync might be the prominent wait event here. Doing the math, the 7 million, it all works out. 15 minutes times 60 seconds times the 8,000 transactions per second is roughly the 7 million. So this actually means, and I'm going to come back to that in a minute, that we're executing 8 transactions per millisecond, roughly 8 transactions per millisecond. Now, the issue is not the number of waits here. The issue obviously is the average wait time. This was an Exadata environment with everything on ASM, so this seems very high, 14 milliseconds. Even with data guard configured, this is not what you would want to see. So the question that we now have is, might logwriter be too busy? Because what does a log file sync involve? A log file sync involves that we are asking the logwriter to flush the redo log buffers, including the commit records that are in there that we've posted in there. And the log file sync might be dominated by the work that the logwriter has to do. So it's either too busy, it may have a CPU issue, or it's experiencing bad I/O service times of the parallel log file writes that it's performing, or there might be an issue in the data guard related work that needs to be done now when we commit in the sync affirm mode. Yeah. So what we're going to do in a minute is we're going to visit the top background events. The top background events will give us answers to these kinds of questions. But we're not going to do that. We're first going to visit the time model. But I can now use the time model to answer one of the questions. Is logwriter CPU bound? Now remember, in the time model shows me the aggregate background CPU time, 580 seconds. This tells me that logwriter is very likely not experiencing a CPU issue, because we are talking about a 15-minute interval here, which is 900 seconds. Yeah. So if this was way over 900 seconds, we might also have to go back and check if logwriter has a CPU issue, but it's way below 900 milliseconds, and this is the aggregate CPU over all backgrounds. So very likely there's not a CPU issue with the logwriter. Yeah. So we're now done with the key areas. How to proceed? Well, there's a single issue here, 14 millisecond log file sync wait events. That's the issue here. The major contributor of this could be the log file parallel write performance, or the sync affirm data guard related processing that has to happen when we commit and start waiting for the log file sync wait events. Yeah, so now we're going to the background wait events. That's the obvious spot to go to from here. In the background wait events, we see the log file parallel write, and it's performing sub-millisecond, 0.96 milliseconds. Well, okay, clearly log file parallel writes are not the issue. In the top background wait events, I have an easy way to spot the other wait events that are related to data guard. Look at the number of times the logwriter performs a write event. That's also the number of times we're shipping redo to the other standby environment. Yeah, so I have 1, 2, 3, 4 other wait events that happen the same number of times, and they are all the ones that have to do with data guard. Redo transport misc, sync remote write, writer remote sync notify, LNS wait on logwriter. Well, let's look at the wait events of those. Well, even if we were to sum up them all, that still brings us up only to 6 milliseconds. And it's not correct to sum them up all, because some of this is happening in parallel. When we do a local write, we also start shipping the redo log to the remote side. So even if we sum these up, we can still not explain the 14 milliseconds that the log file sync is taking. So what now? Well, these other wait events and even the log file parallel write, they have some serious outliers. They're not very stable in terms of performance for each time they take place. There are some serious outliers for these wait events. And what we have here is a critical background, log writer in this particular case, and the other involved backgrounds for shipping the redo to the remote site. When they experience an outlier, that will cause a growing convoy of foregrounds to also get stuck. And when these outliers cause a growing number of foregrounds to also get stuck, that starts magnifying the average wait times of the foregrounds. And I have a visual in a minute that I want to show you to explain exactly how this works. But let's first make this a more simple case so that I can have a simple visual. Let's oversimplify and assume we don't have data guard. And let's further assume that log file sync is determined mainly by the log file parallel write performance. So we're going to ignore any CPU involved. It's mainly log file write time that's determining log file sync foreground wait event. And we have 8 foreground transactions per millisecond, which is what we have in this case. We had 8,000 per second, so 8 transactions per millisecond. And the background log file parallel write normally takes 1 millisecond, but we have one outlier that takes 10 milliseconds. Let's take this scenario and visualize that. So I'm visualizing that scenario here. On the horizontal axis, I have my elapsed time going on. So I have a milliseconds. I go from 0 to 18 milliseconds here. On the vertical axis, I'm showing the number of transactions that are currently waiting for a log file sync. Yeah? Now, every millisecond, 8 new transactions arrive that have performed a commit. 8 new transactions arrive that start waiting for a log file sync. Yeah, so I'm starting to see a growing number of sessions waiting for a log file sync. At some point, the log file parallel write succeeds. And actually, so this is really oversimplified because this log file parallel write actually completes the commit records that were here, that were in the millisecond prior to this millisecond. But the oversimplification works in terms of making my point. So, and then I have another 8 transactions starting to build up and waiting for the log file parallel write to complete. Yeah, and I have this going on for 8 milliseconds. Then I have an outlier. Then I have a log file sync. Sorry, I have a parallel log file write that suddenly takes 10 milliseconds. During that 10 milliseconds, I have a convoy of 80 foreground sessions that start waiting for the log file parallel write to complete for them. Yeah, so this grows and grows, and all these foregrounds start waiting for log file sync. Now the area under the curve represents the foreground wait time. If I have 8 transactions building up, let's say arriving uniformly in this millisecond, those 8 foregrounds will have waited 4 milliseconds. Yeah? And I have 4 milliseconds going on here, and I have 400 milliseconds going on here. Now, what's up to this time frame, 8 milliseconds? What was the average background wait time for the parallel log file write? Well, I had 8 parallel log file writes. They all took 1 milliseconds. So the average background log file parallel write was 1 millisecond. The average foreground wait time, I have 8 times 4, 32 milliseconds in total of wait time over the transactions. How many transactions were there? Well, 8 times 8, 64 transactions. Divide that, I have an average wait time of 0.5 milliseconds of a foreground waiting for a log file sync to complete. Let's do that calculation when we're here. If we're here, my average background wait time is now 18 divided by 9 because I have 18 milliseconds of elapsed time and I've had 9 log file parallel writes. So my average background wait time has now gone up to 2 milliseconds, the average. The average foreground wait time has gone up, well, again, take the surface area under the curve, 32 plus 400, divided by 18 times 8 transactions per millisecond, divided by 144. My average foreground wait time has gone up to 3 milliseconds. So what's the result of this outlier? The result of that outlier is that the background wait time has gone up by a factor of 2, but the foreground wait time has gone up by a factor of 6. This is what background outliers of a critical background process that cause foregrounds to stack up and start waiting due to the average wait time of those foregrounds. They explode, they magnify the wait times. Yeah. So the outliers in the log file writer cause the average foreground log file wait sync times to go up to 14 milliseconds and become the dominant component of DB time in this particular case. I actually did the math for this in much more detail using the histogram information, using Excel spreadsheet, and it explains it fairly good. I can come up almost to the full 14 milliseconds. So in this case, the advice is, well, investigate why you have these outliers for those background wait events, for the log writer and for the data guard background related processes. Improve the quality of service of that path from the primary all the way to the standby, all the way to the disk, since we're doing in a firm, sync-affirm, we're running in sync-affirm mode for that redo destination. Yeah, so that's the point that I wanted to make with using this visual. I hope I've succeeded in that task. It's a bit difficult since this is a one-way of communicating here. Right now I can't see or speak to the audience, but this basically has been my presentation that I wanted to give here at OTW World. And with that, I will conclude and thank you for your attention. I think it's beer time at your place right now. Thank you very much.